Okay, here we are. Squeaky chair. So, we know how this works. I think that you are just asking me to record this because you lack self confidence. I think you know it. Anyway, ATP PCR. We're going to need to know the rate limiting enzymes for all of these. I don't get to edit the page while I'm recording. Whatever. Okay. So ATP PCR, right, lasts for just a few seconds, drops off heavily. Okay, call it 15 seconds, call it whatever you want. I guess they have this crossover right around like 15. That's what he's been saying, right? Like 3 to 15, whatever. So we are limited by creatine kinase because of the ADP. The phosphate group has to bind with the phosphocreatine and creatine kinase, add that phosphate back to the ADP to become ATP, right? Um, then for the short term, this is where we were talking this afternoon. It's more specifically than the glycolytic system, the anaerobic portion. And that was, I think, where we had confusion initially. Because it looks like this whole thing is glycolysis, which it is. But this is aerobic glycolysis. So the difference here is that this pyruvic acid goes to lactic acid. That's just how it happens by default. So when in the presence of oxygen, it can turn into acetyl-CoA. And acetyl-CoA is our key. That is our key to oxidative metabolism in general. Fats, they also become acetyl-CoA through beta oxidation before entering the Krebs cycle and the electron transport chain. 33 ATP, 10 times as great as the 3 that we would get from glycogen or the 2 that we would get from glucose. And yada, yada, yada. Um, so this long-term energy system is our oxidative system. It's both fats and carbs. The oxidative system plays into this anaerobic glycolytic system. It's really just an extension. We're performing this process at first, and then once our body gets the oxygen delivered to the cells, then we can go on to the much more efficient entire process. Um, yeah, and that's right here. So this is something, this he could have this exact thing on the test. This was in our notes. I gave us a little cheat code right below it. So if you're ever like, oh, what the hell is it? It's right here. But this just explains the whole process, right? So we get our glucose. Let's just go through it. Why not? You've got hours. You've got hours. Okay, glucose is absorbed here. Goes through the cells, rada, and at rest, we should just pack it into glycogen, or we'll pack it into fat, but generally glycogen. And then down here, we're gonna, if we need exercise, if we need it immediately, we're gonna go right to glycolysis. So from glycolysis, we end up with glucose 6-phosphate into pyruvic acid. So pyruvic acid is right here. This blue box should just be lactic acid. I don't know why it has two different, I guess it's different places. Because remember, lactic acid has 3 functions. It can be used there, it can be transported away to be used, or it can, oh, wait, I might need to remember this. I'm sure you have this down. You wrote it down last night. The 3 functions of lactic acid. Blah, blah, blah. And here we have lactic acid goes into pyruvate, which goes back into glucose. Glucose is our end goal pretty much everywhere, so we can use it for energy. So, so when we have oxygen, this pyruvate is going to be converted into acetyl-CoA. That's our key. That's our key. We need acetyl-CoA to enter oxidative phosphorylation, citric acid cycle, Krebs cycle, aerobic glycolysis, all the same thing. It's all oxidative. So, yeah, convert it to acetyl-CoA first. And yeah, here, you already know all this shit. And hey, in case we're talking about muscles and we're talking about proteins in the muscle, I don't know if you had trouble with this, but troponin versus tryptomyosin, their function, the easiest way I can remember it is tryptomyosin is already on the myosin. It starts as part of the, myosin actin, you know, caulking head process, whatever the fuck the, what's it called? Cycling, coupling, excitation coupling, whatever. Um, so tryptomyosin is the one that's already on the myosin, and troponin removes it. It's in the name. I don't know if you had trouble with that, but I missed that on the first quiz regarding this. I answered troponin when the answer was tryptomyosin. Anyway, so we got through all that, and then EPOC. EPOC is basically just what happens because of imperfections. I mean, think about it like this. If we've got cells moving at a set speed all the way through our body, and then all of a sudden we have an incredible demand on those cells to work harder, doesn't happen immediately. That would be fantastic, but we're not quite that efficient. We can get better efficiency. So our curve looks like this. When the intensity and the demand goes up right here, we get there a little slower. With training, remember, this line will look a little bit closer. Our oxidative system becomes more efficient at just running. But no matter what we do, we're going to have some level of oxygen that was needed for all of that energy that we produced immediately. That's going to have to be burned off. So that is the EPOC. And if you think about it like this, if you think about it as, I just think about it as the shape, really, because you're if something didn't happen here, it has to be made up for on the tail end. So we're just gonna take this shape and flip it, really. I think this is maybe a little exaggerated, but also because our heart rate is higher, we're naturally gonna have more demands for oxygen. So maybe that's why this one has a larger area than this. But just remember that our bodies aren't perfect machines, so there's a slight period of ramp up when our systems get going to their to the demand. Yeah, I, I really think you got this. I think I got this. I think we got this. I'm gonna share with you a document of notes that I took during the class session today that we were just reviewing. The stuff that he was talking about, the questions people asked. Yeah. Good luck in the game. Unless you already had it. Either way, whatever.